Hello, this is Dr. Joe Trout at the Physics Program at Stockton University. And this lecture is going to cover two chapters, chapter 21 and 22. We'll talk about the birth of stars and the discovery of planets outside our solar system. In this first picture, we show where stars are born. And we see a close-up of part of the Carina Nebula, and it's taken with the Hubble Space Telescope. And what we're seeing are these jets powered by newly formed stars embedded in a great cloud of dust and gas. And parts of the clouds are actually glowing from energy of the very young stars that recently formed within them. So why this dust and gases are important is that this is what the planets and stars are formed from. So gravity causes the dust and the molecules of gas to be attracted to one another, and they get larger and larger, and through the compression from gravity, they begin to warm up. If gravity can cause this mass of dust and gas to heat up large enough to fuse hydrogen, then they'll become a star. So what we see here are, once again, Hubble Space Telescope images and the central regions of M16. This is also known as the Eagle Nebula. And it shows these huge columns of cool gas. In these gases is, of course, hydrogen, which is the most abundant molecule in the universe. And these columns are higher density than the surrounding regions, and they have resisted evaporation by ultraviolet radiation from a cluster of hot stars just beyond the upper right-hand corner of the image. So the tallest pillar is about 1 light year long. Don't forget, a light year is the distance it takes light to travel in a year. And this region is about 7,000 light years away from us. In B, we see a close-up view of these pillars and some of the very dense globules. And they harbor the embryonic stars, right? So the beginning of these stars. Astronomers coined the term evaporating gas globules, or eggs, for these structures, right? So the eggs that start to form the stars. And in part, so they could say that we found eggs inside the Eagle Nebula. And it's possible that because of these eggs are exposed to the relentless action of radiation from the nearby hot stars, that some may have collected enough material to form a star. So you're probably becoming very familiar with this picture. Here we see the Orion star group, which was named after the legendary hunter in Greek mythology. And the three stars that are together linked in Orion's belt was supposed to be the image, which was imagined to be the image of a sword hanging from Orion's belt. And the object in the end of the blue lines in the sword is the Orion Nebula. So if you look at, and this was taken with visible light, so picture A was taken with visible light. If we look at B, this is an infrared image, so in essence showing the heat, if you will. And this is wide-angle infrared view of the same area was taken with an infrared astronomical satellite. So the heated dust clouds dominate this picture, and don't forget this is a false color image. So The white and the red show hotter areas, but these are, we can't see infrared images. And many of the stars that stood out on the part A are now visible. An exception is the cool red giant star Betelgeuse, and which can be seen as the yellow point in the left vertex of the blue triangle in Orion's armpit. So if we look right around, um, if we look at this image here, we can see where that star was and how and we can barely see it in the infrared image, right? So this infrared image lets us see how large and full of cooler material the Orion molecular cloud really is. So on the visible light image to the left, you see only two colorful regions of interstellar matter, and the two bright colored splotches are at the end of just below Orion's belt. The lower one is the Orion Nebula, and the higher one is a region of the Horsehead Nebula. So here we see the Orion Nebula shown in visible light, and in B we see the near infrared radiation, and we can see more detail within the dusty nebula, since the infrared can penetrate the dust more easily than we can see with visible light. So these two pictures show the center region of the Orion Nebula, and the Orion Nebula harbors some of the youngest stars in our solar system, or in our neighborhood. And at the heart of the nebula is the trapezium cluster, and this includes 4 very bright stars that provide much of the energy that causes this nebula to glow so brightly. So in these images, we see that a section of the nebula in A, visible light, and B um, is in infrared. And the 4 bright stars in the center of the visible light image are the trapezium stars. Most of the stars seen in the infrared image are completely hidden by the dust in the visible light image. So here we see a young cluster of stars, and it's formed within the Carrion star-forming region about 2 million years ago. Here we see stellar winds and pressures produced by the radiation from the hot stars within the cluster, and they're blowing out and sculpting the surrounding gas and dust. And this nebula still contains many globules of dust, and stars are continuing to form in this and within the denser globules and the pillars of the nebula. This is a Hubble Space Telescope image, and it includes near-infrared exposure of the star cluster and visible light observations of the surrounding nebula. If you notice, colors in the nebula are dominated by the red glow of hydrogen gas and blue-green emissions from glowing oxygen. So how does this all work, right? If we look at the propagating star formations, we see that the star formations can move progressively through a molecular cloud, right, which has gas and dust. And the oldest group of stars lies to the left of the diagram and has expanded because of the motion of the individual stars. Eventually, the stars in the group will disperse and no longer be recognized as a cluster. The youngest group of stars lies to the right, and next to it is the molecular cloud. And this group of stars is about 1 to 2 million years apart, or 1 to 2 million years old. The pressure from the hot ionized gas surrounding these stars compresses the material in the nearby edge of the molecular cloud, and it starts to initiate this gravitational collapse and will lead to the formation of the stars. So we see that we get gravity to start pulling things together, right? And we end up with these protostars, and now they have gravity, and they're moving, or they're located near these molecular clouds. And we see that we can get some compressed gas due to the surrounding stars, and these stars will become larger and larger as they pick up material. So if we look at a formation of a star, first we start with A, and this is a dense core um, from within a molecular cloud. So we have a cloud that consists of dust and molecules of gas, and we get a core to start up. And this is about 5,000 astronomical units. And don't forget, an astronomical unit is the distance from the sun to the earth, roughly. So then we see a protostar with a surrounding disk of material forms in the center of the dense core, and it's accumulating additional material from the molecular cloud through a gravitational attraction. In C, we see that a stellar wind breaks out, but it's confined to this disk flowing out along the two poles of the star. So eventually, the wind sweeps away the cloud of material and halts the accumulation of additional material. And a newly formed star surrounded by a disk becomes observable. And these sketches aren't drawn to the same scale, so don't forget the first picture is about 5,000 times the distance between the sun and the earth. And this final new star is about 100 astronomical units. So here we see these gas jets that are flowing away from a protostar. So we see these pictures show the neighborhood of a protostar known as HH34 because it's a Herbig-Haro object. And this star is about 450 light years away and only about 1 million years old. And light from the star itself is blocked by the disk, which is larger than 60 billion kilometers in diameter. And we're looking at it edge on. So the jets that are emerging perpendicular to the disk, and the material in these jets is flowing outward at speeds of about 5.8 times 10 to the fifth kilometers per hour. So this series of these three images show changes during a period of about 5 years. And every month a compact clump of gas is ejected, and its motion outward can be followed. And the changes in the brightness of the disk may be due to the motion of clouds within the disk that alternatively block some of the light and then let it through. So here's two more pictures of HH47, HH1, and HH2. And These were taken with the Hubble Space Telescope, and once again show these jets flowing outward from these newly formed stars. And in the HH47, the top image, a protostar of about 1,500 light years away. So if we look at the disks around these protostars, this is once again our Hubble Space Telescope infrared images, and they can show the disks around these young stars in the constellation Taurus. And in a region of about 450 light years away. In some cases, we can see the center star or stars because some of them are binary, and in other cases, the dark horizontal bands indicate that regions where the dust disk is so thick that even infrared radiation from the star can't make it through the clouds. So the brightly glowing regions are starlight reflected from the upper and lower surfaces of the disk, which is less dense than the central portions. So if we look again at the HR diagram, we can see the evolutionary tracks of the contracting protostars. So don't forget, what we're saying is that there's a bunch of dust and gas out there, and it gets condensed, and gravity increases and starts pulling it in further and further, right? And as it's compressed, it heats up, and so we can see what's going on here. So if you look at the tracks are plotted on the HR diagram to show how the stars of different masses change during the early parts of their life. So don't forget, on the y-axis is luminosity, and on the x-axis is surface temperature, but don't forget, the highest surface temperatures are at the origin, and temperature decreases as we move out. So if we look at the stars of different masses and how they change from the early parts of their lives. So the number on each of the disk points of the track is roughly the number of years it takes for the embryo star to reach that stage. And the numbers are the result of computer models and are therefore not well known. Note that the surface temperature on the horizontal axis, as we said, increases to the left, and you can see that more mass a star has, the shorter time it takes to go through each stage. So here we see a 100 mass solar star, and in about 100 years it ends up here, and in about 1,000, and then 10 to the fourth. And what we see is that as we move down, we see that there's a 10 molar solar mass star and a 3 solar mass star, and down to a 0.1 solar mass star. So it's a tenth the size of our sun. So note that the surface temperature on the K horizontal scale is increasing towards the left, and you can see that the more mass a star has, the shorter the time it takes to go through each stage. And the stars above the dash line are typically still surrounded by infalling material and are hidden by it. So you might think the larger the star is, that the more mass it has, and therefore it has more energy to burn, so it would take longer to reach the the main sequence, which is, by the way, where we'll start we'll call that zero age when it reaches the main sequence. But this isn't true, right? The larger it is, the faster it ends up on the main sequence. So here we see some pictures of disks surrounding protostars. So once again, these are Hubble telescope images, and they show 4 disks around these young stars in the Orion Nebula. And the dark, dusty disks are seen silhouetted against the bright backdrop of the glowing gas in the nebula. So the size of each of these images is about 30 times the diameter of our planetary system. So this means that the disks we see here range in size from 2 to 8 times the orbit of Pluto. The red glow in the center of each of the disks is a young star no more than 1,000,000 years old. And these images corresponded to the stage in the life of the protostar, is shown on a previous picture. So here we see protoplanet disks around 2 stars. So if we look at the left view of each of the stars shown, is infrared observations by the Hubble Space Telescope of their protoplanetary disks. And the central star is much bigger than the surrounding disk. So the instrument includes a coronagraph, which has a small shield that blocks the light of the central star, but allows the surrounding disk to be imaged. So for instance, say you wanted to look at the sky towards the east in the morning, but if you look in the sky towards the east, what you'll see is the very bright sun, and you won't really be able to see the the rest of the sky very well. But if you take your hand and put it over the sun, then you can see the rest of the sky. So that's what these pictures are showing. So if we look at these dust rings around the young star, and this image was taken by ALMA, and it's at a wavelength of about 1.3 millimeters, and it shows the young star and its protoplanetary disks. And if you can see that there's multiple rings like we've seen before, and the gaps indicate that there's presence of emerging planets. So as these planets sweep through the dust, it picks up the dust and sweeps out the area clear of the dust. So when we're trying to detect planets, one way to do it is to detect the Doppler motion of the stars. So don't forget, if we have the motion of a star around a common center of mass, and an orbited planet can be detected by measuring the change in the speed of the star. So when the star is moving away from us, the lines of the spectrum show a tiny red shift, and when they're moving towards us, they show a tiny blue shift. So this change in color or wavelength has been exaggerated here, but really it's a tiny effect. And this Doppler shift we measured are extremely small and require really sophisticated equipment. So this stars being, don't forget, whenever we have 2 masses, there is a force of attraction between them. Okay, and what we see is that the force is equal and opposite. So what we see is that the planet will have an effect on the stars, and we'll see this slight wobble in their motion, And we can detect this wobble by using the Doppler shift. So in 1995, we see that two astronomers of the Geneva Observatory, and they were first to discover a planet around a regular star. And they are seen here at the observatory in Chile, where they continue to do their planet hunting. So here we see a artist's impression of a hot Jupiter-type planet orbiting close to a sun-like star. And this artist shows bands of the planet like Jupiter, but only estimate, but we only estimate the mass of the most hot Jupiter-type planets from the Doppler method, and don't know what conditions on the planet are like. So this Doppler shift method is really only good for really large planets. Another way we can find planets is by looking at the planet transits. So as the planet transits, it blocks out some of the light from the star, causing a temporary dimming of the brightness of the star. And this top figure shows three movements through the transit, right? So first, when it's away, when it's not in direct line with our observation, like in position 1, then the star is really bright. As it starts to move to position 2, we see that this transit's ingress in which the planet is beginning to cross the star, which means there'll be a dip in the brightness of the star. And finally, as the star goes to position 3, as the planet goes to position 3, it completely blocks out some of the light from the star. And then as it goes to exit, goes past the star, we see the same thing happening on the other side in reverse. So here we see this box is shown a region where the Kepler spacecraft cameras took images of over 150,000 stars regularly. And it was trying to find these transient planets. Here we see exoplanets around HR 8799, and this image shows the Keck telescope's observations of 4 directly imaged planets orbiting HR 8799. And a size scale for the system gives the distance in astronomical units. So if we look at the discoveries of planets through 2015, the vertical axis shows the radius of each of the planets compared to Earth. So here's would be planets with the radius the same size as Earth, and 4 times the size, and 10 times the size, and 20 times the size. So though this is a logarithmic scale. And the horizontal axis shows the time it takes each planet to make one orbit, given in Earth days. Right, so recall that Mercury takes about 88 days and the Earth takes a little more than 365 days. So the yellow and red dots show planet discoveries by transits, and the blue dots are the discoveries by radial velocity using the Doppler technique. So what you notice is by the transits we're able to find the smaller planets that have also the shortest orbital periods. And with the Doppler method we can only see these larger planets. It's only useful for these larger planets. So if we look at the Kepler discoveries, This bar graph shows the number of planets of each size range found among the first 2,213 Kepler planet discoveries. And the sizes range from half the size of the Earth to 20 times the size of the Earth. And on the vertical axis, you can see the fraction that each size range makes up of the total. And note that the planets are between 1.4 and 4 times the size of the Earth, make up the largest fraction. And note that this size range is not represented among the planets in our solar system. So here we see size distributions of planets for stars similar to the Sun, and we show that the average number of planets per star in each of the planet size range. And this distribution is corrected for biases in the Kepler data and shows the Earth-sized planets may actually be the most common type of exoplanets. So of the exoplanets that we are pretty certain about their densities, these exoplanets with known masses and radii are in red circles are plotted along with solid lines to show their theoretical size of pure iron, rock, water, and hydrogen planets, and with increasing masses, right? And the masses are given in multiples of Earth masses. So for comparison, Jupiter contains enough mass to make 320 Earths. And the green triangles indicates planets in our actual solar system. So if we look at the exoplanet system for Kepler-62, and with the solar system sizes to the same scale, so the green areas are the habitable zones, and they range of distance from a star where the surface temperatures are likely to be consistent with liquid water. So this is a painting commissioned by NASA, and it conveys the idea that there may be many planets resembling Earth out there, and our methods for finding them are improving. So now we know that we had to look quickly at how these stars begin to form and how planets begin to form. So during the later stages, this is the Ant Nebula, and during the latest phases of stellar evolution, these stars expel some of their mass, which returns to the interstellar medium to form new stars. So the Hubble Space Telescope image shows the star losing mass, known as Menzel 3, or the Ant Nebula. And this beautiful region of expelled gas is about 3,000 light years away from the sun. And we see that there's a central star that has ejected this mass, preferential in two directions. And the object is about 1.6 light years long. And the image is color-coded, and red corresponds to emission lines of sulfur, and green to hydrogen lines, and green to nitrogen lines, and blue to hydrogen lines, and blue-violet to oxygen. So we can tell what these clouds are made out of. So the stars, as they start to form, we say these star layers during and after the main sequence. So at first what we have is we get these stars to start to compress, and we end up with, if there's enough heat, we'll see hydrogen beginning to fuse. So in figure A, what we see is that during the main sequence, a star has a core where fusion takes place in a much larger envelope that is too cool for fusion to take place. And in B, when the hydrogen in the core is exhausted, so it becomes mainly made up of helium, not hydrogen, then the core is compressed by gravity and heats up. This additional heat starts the hydrogen fusion in the outer layers. Note these aren't drawn to scale, right? So if we look at the relative size of the stars, right, this image compares the size of of the sun to that of Delta Bootis, a giant star, and Psi Cygni, a supergiant. And note that the supergiant is so large in comparison to the other two stars that only a tiny portion of it is shown in the frame. So if you look at Betelgeuse, it's in the constellation Orion, and the Hunter, and in the right image is marked with a yellow X, um, right, is marked with a yellow X near the top. And in the left image, we see that this is an ultraviolet with a Hubble image taken with the Hubble Space Telescope. And in the first direct image ever made of the surface of another star. And as shown in the scale on the bottom, Betelgeuse has an extended atmosphere so large that if it was in the center of our solar system, it would stretch past the orbit of Jupiter. So once again, if we see the sizes of these stars and the evolutionary tracks of the different masses, and the solid black lines show the predicted evolution from the main sequence through the red giant or superstage of the HR diagram. And starting with what happens at zero age, which is on the main sequence. So don't forget, this is the surface temperature, and it's increasing in this direction, and this is luminosity. And what we see is that if we have a 15 solar mass star, and it will begin to move out this way and start to cool off. Right, so this is at time 0, and then after it's spent its time on the main sequence, it will start to change. So the numbers shown are how many years each star takes to become a giant after leaving the main sequence. And the red line is the zero age main sequence. So here we see Omega Centauri, and it's located about 16,000 light years away. And it's the most massive globular cluster in our galaxy, and it contains about 7 million stars. If you look at B, this is an image taken with the Hubble Space Telescope and is zooming into the center, to near the center. And this image is about 6.3 light years wide. And the most numerous stars in the image, which are yellow-white in color, are main sequence stars similar to our sun. And the brightest stars are the red giants that have begun to exhaust their hydrogen fuel and have expanded to about 1,000 times the diameter of the sun. And the blue stars have started helium fusion, which means now we're hot enough to start to fuse helium. So if we look at NGC 4755, this is an open cluster of young bright stars, and it's about 64,000 light years away and away from the sun. And note the contrasts in the bright yellow supergiant and the hot blue main sequence stars. And this name comes from John Herschel's 19th century description of a casket of various colored precious stones. So this was the jewel box. So when we talk about a globular cluster, it's one of about 150 spherical star clusters, each with hundreds of thousands of stars, and they form a spherical halo around the center of our galaxy. If we look for an open cluster, this is a comparatively loose cluster of stars containing from a few dozen to a few thousand members, and these are usually located in spiral arms or disks of our galaxy. And finally, there's an association, and this is a loose group of young stars whose spectral types and motions and the position in the sky indicate a common origin. So if we start for these groups of stars, we start with an association, that's the smallest group. Then we go to an open cluster, that's a little bit larger, and then a globular cluster, which is the largest grouping of stars. So here we see the young cluster HR diagram, and we see that the HR diagram from a hypothetical young cluster with an age of about 3 million years. And note that the high mass, which is high luminosity, stars have already arrived at the main sequence stage of their lives, while the lower mass stars are still contracting towards the zero age image, the zero age main sequence, or this red line. And they're not yet hot enough to derive their energy from the fusion of hydrogen. So you see this young cluster NGC 2264, and it's located about 2600 light years from us. And this is a region of newly formed stars known as the Christmas tree cluster. And it's a complex mixture of hydrogen gas, which is ionized by the hot embedded stars shown in red. And the dark dust lanes that obscured and dark obscuring dust lanes and the brilliant young stars. And this image shows the scene about 30 light years across. So if we look at this cluster, we compare this HR diagram to that in 22.8, and although the points are scattered a bit more here, the theoretical and observational diagrams are remarkable and satisfyingly similar, right? So they kind of look what we expect it to look like. So all the stars in this open star cluster, like NGC 3293, form at about the same time, and the most massive stars, however, exhaust their nuclear fuel more rapidly and hence evolve more quickly than the stars of low mass. So as the stars evolve, they become redder. And the bright orange star is a member of the cluster that has evolved most rapidly. Right, so the lifetime of these stars and how long they spend on the main sequence depends not on how much fuel they have, but on how fast they're burning the fuel. Right, so you can think of it as for instance, if you fill your tank with gasoline, right? If you move at a normal speed, you'll be able to go further than if you go really fast. And the reason is going really fast burns more fuel quicker. So we see as the more massive stars often or have a shorter lifetime on the main sequence. So here we see cluster M41, and it's older than the previous cluster, and it contains several red giants, and some of its more massive stars are no longer close to the zero-age main sequence. So this ground-based photograph shows the open cluster 41, and note that it contains several orange-colored stars, and these are stars that have exhausted their hydrogen centers and have swelled up to become red giants. And here we see the HR diagram for a hypothetical old cluster of about 4.2 billion years. And note most of the stars in the upper part of the main sequence have turned off towards the red giant region. And the most massive stars in the clusters have already died or are no longer on the diagram. So this is the HR diagram for a globular cluster 47, and note that the scale of luminosity differs in that of the other diagrams in the chapter. So we are focusing only on the lower portion of the main sequence and the part where the stars remain in this old cluster. So note this only goes up to a luminosity of about 100 times the size of the sun and surface temperatures around 3,000 to 6,000. So if we look at clusters of different ages, right, this sketch shows how the turnoff point and the main sequence gets lower as we make the HR diagram for clusters that are older and older. So here's a newborn cluster, and then about 1 million years and about 10 billion years. So if you look at the evolution of the stars like the sun on the HR diagram, each stage in the star's life is labeled. So if we look at A, the star evolves from the main sequence to become a red giant, decreasing in surface temperature and increasing in luminosity. So it gets colder and brighter. And then in B, a helium flash occurs, leading to a readjustment of the star's internal structure. And we see a bright flash. And in C, a brief period of stability during which helium is actually fused into carbon and oxygen inside the core. So now our things are hot enough to actually fuse carbon and oxygen. And in D, after the central helium is exhausted, the star becomes a giant again, and it moves to a higher luminosity and even lower temperature. But by this time, however, the star has exhausted its inner resources and will begin to die. And where the evolutionary track becomes a dashed line, the changes are so rapid that they're difficult to model. So don't forget, this was all done with modeling. Okay, so if we look at the lower layers inside a low mass star before death, here we see that the layers, we start with a carbon oxygen core, and then we have helium fusion going on, and then we have a helium core, and then hydrogen shell fusion and a hydrogen envelope, right? And as we go, these include from the center outward, from the carbon oxygen core, a layer of helium hot enough to fuse, a layer of cooler helium, a layer of hydrogen hot enough to fuse, and then cooler hydrogen beyond. So here we see a gallery of planetary nebula, and if you look in the book, you can see exactly which one of these, which of these they are. And we'll also talk more about the shape of the actual nebula that we'll see. All right, well, thank you for your time.